This one here. Okay, welcome everybody. We are ready for our first California Dreams Technical Seminar Series seminar of May of 2025. I hope lots of people are enjoying nice spring weather. We are very lucky to have with us today John Hacker from Teledyne Scientific. Teledyne Scientific is one of the 3 DoD volume fabs that we have in California Dreams that we're very happy to be working with. And we are especially happy to be working with John, who's a department head there at Teledyne Scientific, involved in R&D efforts in 3D-HI, indium phosphide MMICs, and other technologies. John received his Ph.D. in electrical engineering at Caltech, keeping things within the hub. And I just recently learned, but it didn't recently happen, that John is a fellow of the IEEE. So John, thank you again for coming to join us today, and please take it away.
Thank you, Steve, for that introduction. Okay, today I want to present information on Teledyne Scientific's 3D-HI foundry process that we call SLIC. This has been in development here for quite some time, and we are looking forward to being able to offer it ultimately through the California Dreams Hub. So with that, let's proceed. My talk will be broken into 3 sections. First, a very quick introduction to Teledyne Scientific. Then I want to look at some detail in packaging needs that are important for specifically targeting millimeter wave transceivers and phased arrays. And then I want to introduce and discuss Teledyne's SLIC foundry process and how that particular process addresses the needs discussed in part 2. Okay, so Teledyne Scientific, formerly Rockwell Science Center, is located in Thousand Oaks, California. The building was opened in 1963, so we have quite a long history here of advanced R&D, and in particular, a 40-year history of working on advanced semiconductors and MEMS technologies. Management calls this a high-mix facility. That's another way of saying R&D, I think. But we specialize in non-CMOS semiconductors, so primarily 3-5, indium phosphide, originally GaAs, and lately also gallium nitride, along with MEMS technologies, which primarily are silicon-based. We do also have expertise in vanadium dioxide, which is an interesting phase change material for some switching applications. We have a very experienced staff here, both covering engineering and operations, and we support R&D, prototyping, and low-volume DoD-type production. Our microfabrication activities can really be broken down into 3 kind of principal areas, the largest of which is primarily focused on government-sponsored contract R&D. This is often work funded by both DARPA and the Tri-Services, and it's where most of our technology is born. And whether or not that technology survives to become offered as a foundry process or a technology for customers really depends a lot on how successful that initial R&D activity is. If it does show promise and has a customer base that we can look at to address and get a return on investment, then it would be moved to a foundry development process, which is the center portion of this chart. And here, what we try and do is mature the technologies, develop, statistical process control monitoring, and work instructions that support a standalone foundry process, along with, of course, the development kits and so on that are needed for people to use it. And this ultimately is a product that we would release to the hub, assuming that the hub had also an interest in that technology. We also offer here on the third column on the right, basically pure clean room fab services. And this allows customers who maybe have a process that they have developed perhaps at a university or a lab that doesn't have a full tool set, and they want to process that lab, but keep it to themselves, not, it's not IP that Teledyne owns, then we can offer our tool set and our operators to work with that company to develop a process or even partially develop a process. Maybe they only need access to a certain part of our tool set, and we can support that as well. In terms of our microfabrication capabilities, in particular our high-performance Foundry IC processes, we offer a number of technologies. These technologies are available both in dedicated runs and in some cases in multi-project wafer runs, particularly the indium phosphide HBT on the left. So that's our most mature and most fabricated process, in particular the indium phosphide HBT 250 nanometer process. Has an MRL of 8. We offer MPW runs, several of them during the year. This will also be offered through the Dreams Hub. And we also offer products that are made using this technology. In particular, we have a line of millimeter wave and submillimeter wave power amplifiers that we sell, and which are found in a lot of test and measurement equipment. You may not know it, but our stuff is inside a lot of test and measurement equipment. The indium phosphide hemp process, a little less mature, MRL 7 for the 500 nanometer, MRL 5 for the 50 nanometer. This is primarily a low noise amplifier technology, and we find that customers who wish to use this technology are typically looking at very high frequency, low noise front end challenges. Our gallium nitride hemp process is emerging. We don't offer a what I'd call legacy GaN hemp process. We do things a little differently. We're doing a charge enhanced hemp process, which offers a substantially better linearity than the legacy GaN hemp. And that has attracted interest from a number of people who want to improve the efficiency of their GaN hemp power amplifiers. And then finally, the focus of this talk on the rightmost column, the silicon RF interposer process, which we call SLIC. And this is really a 3D HI packaging process that is designed to work specifically for millimeter wave transceivers and phased array applications. And finishing up on the introduction to Teledyne Scientific, just a little discussion about the clean room tools that we have here. We have a 6,000 square foot class 100, class 1000 clean room. There's a dedicated fab ops staff that operates and is trained on all of the tools. All tools are subject to PCM and SPC management, so they can be used reliably and repeatedly. As we also have a number of semiconductor and MEMS device engineering groups here that basically design into this fab ops groups tools and tool sets to develop new technologies and to mature the ones that we think are to be offered as boundary processes. It's a diverse tool set. Most of our work is 4-inch, commensurate with 3-5 wafer sizes. We can do 6-inch, And also we can go down to 2-inch for some of the more esoteric substrates, perhaps aluminum nitride and things like that. Okay, so that's our introduction to Teledyne. Now let's take a little detour and look at what packaging needs make sense for millimeter wave transceivers and phased arrays. So I want to start off with a little phased array refresher, since this is one application area for this packaging technology. And just thought I would give a brief primer for those people who are not so familiar with phased arrays. I know a lot of you are more expert than me on it, but for those that aren't, a phased array is basically a collection of elements in an array, and each element can be individually addressed to adjust its phase and amplitude, both on transmit and or receive. By doing that, you can spatially combine the outputs of these multiple elements into a single beam that points in a specific direction that you can choose based on the phase settings of the individual elements. And this allows you to electronically steer the beam, which is really the one and only point of a phased array. It's the electronic steering, and that is the key advantage. It has lots of disadvantages. From a performance point of view, you get gain drop as you steer off angle. The antenna impedance changes, which can affect the the performance of the PAs and LNAs and so on. And in addition to those performance hits, there's also just the complexity of these systems, the number of elements, the need to individually address them, and the complexity of getting thermal problems out. They get hot, you have to get heat out, a lot of signals in, and so on. So they are challenging, and that has limited their use in the past. But as we're seeing, particularly with some of the new services like Skynet, which has phased arrays in consumer applications, we're now starting to see phased arrays coming into the mainstream of electronics. One thing to note is that the element pitch is typically held at roughly half a wavelength, and that's to avoid grating lobes, which essentially are undesired beams in directions that you don't want to emit. And so that lambda by 2 requirement creates quite a few headaches as you go up in frequency. All right, so the original motivation for the SLIC technology was millimeter wave phased arrays. And this really comes from a very fundamental set of limitations as you go up in frequency for phased arrays or antennas in general. So on the left is the Friis transmit equation. And what you see from that very quickly is that the receive power is proportional to the wavelength squared. So obviously, as you go up in frequency, you're getting a very severe reduction in receive power just from that increase in frequency. And to offset that, you then have to increase your antenna directivity, the D's in the equation. Both the transmit and the receive antennas need to be large so that their directivity can compensate for the reduction in receive power from the reduced wavelength. So that's because of those limitations, millimeter wave systems, phased arrays in particular, require large arrays with a lot of small elements compared to microwave systems. And that results in significant cost and complexity in fabrication. Looking at the right side, the other issue that we have as we go up in frequency is that our antenna element size shrinks as basically 1 over f squared. That's because the pixel area, the element area, needs to be maintained at half a wavelength. So that's the red line on this plot of frequency versus area. At the same time, if we look at millimeter wave electronics, MMICs and such, the Johnson figure of merit basically says that to maintain a fixed output power, your transistor size is going to need to increase roughly with f, the frequency. And so you get this crossover point, roughly in the 30 to 50 gigahertz, 30 to 60 gigahertz region, where the element size is too small to fit the electronics that you need to make that element transmit or receive with the required power and phase and so on. And so that becomes a packaging problem. The solution is, of course, three-dimensional integration. If you don't have enough area, you have to stack your electronics to get everything to fit. And that's really the rationale and the reason why SLIC exists to address these needs. Okay, so if we turn the clock back to roughly 2005, when SLIC was originally envisioned as part of the DARPA initiative called SMART, phased arrays at those times were very rarely used. They were extremely expensive and only on the most high-value military assets, large boats, large ships, fighter jets. These are the only real applications where the cost and and size and power consumption of phased arrays made sense. They were simply too expensive for anything else. And they were all point solutions. They were custom designed for a specific application. And this made them also very difficult to, get your NRE in a high value application and then try and distribute it to lower value assets. It really just didn't work. But at that same time, a number of developments in the microwave, millimeter wave industry were happening that really helped to solve some of these fundamental problems that phased arrays had back then. It's mostly a packaging problem. You have to get a lot of complexity into a small area, and you have to do it cheaply. One way to do that was to leverage the rapidly evolving RFIC technology. People were learning to put a lot of RF functionality into silicon CMOS and SIGI foundry processes. And that really shrank a lot of the electronics that needed to go into these phased arrays. The other area that was needed and which was also rapidly evolving was the batch fabrication process, in particular, batch fabrication of circuit boards and wafers that could support millimeter wave and submillimeter wave transmission lines and so on. And so that by batch fabricating elements, you eliminate the touch labor, you reduce the cost. And then allowing the idea of scalable tiling. So build a small tile, but then put them down like tiles on a floor to make a larger array was another way to assemble large arrays economically. And so these techniques became really the pillars upon which we could build upon the limitations of phased arrays at that time and get them more inexpensive, higher performance, and more available for applications that really couldn't afford the huge costs of the original designs. Okay, so from the standpoint of a millimeter wave package requirements, the minimum requirements you really need are low loss impedance controlled transmission lines, even small distances at millimeter waves on a substrate are electrically long and can really corrupt the signal if you're unable to propagate them correctly. You need fine line geometries, and that's to support dense, compact interconnects. Remember, our half wavelength element size is small, so we got to pack things in, and we can't have large space devoted to interconnects. There's already a space limitation constraint from just the electronics you need, much less the interconnect to make it all work. So That means you need 10 micron minimum or maximum 10 micron line in space, 10 micron vias, 10 micron via pitch. These are all kind of the biggest sizes you could really hope to get away with and still have a viable technology. And then the other aspect of a millimeter package is that you really need heterogeneous integration. You need the RFICs for the back-end electronics, for the digital control, and so on. But you also need the 3.5 performance up front for the bandwidth, for the power amplifier power, for the ultra-low noise receivers. The silicon struggles to be the best there, and so you really need to mix and match both silicon and 3.5s to get the kind of performance that's often required. And then finally, you need through substrate vias, TSVs, for backside signal access, and that allows you to tile the resulting component to make larger arrays. And finally, it needs to be batch fabricatable to minimize touch labor and support scalability, particularly for arrays. Okay, so as inspiration for the SLIC approach, we can look towards the microwave world where commercial X and K band arrays, I mentioned Skynet, but there's others as well, have really broken a lot of ground on making inexpensive phased arrays. And they've done it using primarily multi-layer micro-via RF laminates, printed circuit boards, and using ball grid arrays and QFN packages, which work pretty good in the microwave world and are compact and small for the digital, and also for microwave and millimeter wave as well. Those QFN packages work pretty good. And then they also took advantage of advances in the ability to model, simulate, design planar antennas to develop these printed circuit board based phased arrays. A couple of examples shown here. Gabriel Rabiz was a major driver in this area and really revolutionized the application of phased arrays in the microwave area. So why not just make millimeter wave phased arrays out of PC boards? Well, there's some limitations that really make it hard to do that. If you look at commercial microwave PCB-based solutions for phased arrays, they have some pretty tough limitations to overcome. Line and space resolution for PC boards, typically 75 microns. You can push them sometimes to do a little better, but not much. And it becomes very problematic to improve that. Microvias, great at microwaves, but they're about 100 micron diameter, and that's another limitation. Laminate minimum thicknesses, typically 50 microns. You need smaller than that for millimeter wave, or you get substrate modes. And then the minimum VGA pad pitch, 350, 400 microns. QFN is similar. Just limits what you can do in terms of the package to PC board interface. And it really becomes problematic as you get out of the microwave and into the millimeter wave bands. So Teledyne's 3D-HI SLIC packaging technology really exists to bridge that gap, to get past the limitations of printed circuit boards and move into the millimeter wave bands using a similar approach, but with a higher fine line process. Okay, so the other aspect of millimeter wave and sub-millimeter wave packaging is that heterogeneous integration really becomes quite important. Why do we need it? Basically because a single device technology or foundry process limits performance in complex system-on-chip tiles, particularly in the millimeter wave bands and higher frequencies. You know, the silicon backends are great. They permit dense, complex RFICs. They have high yields, and they make total sense for use where complexity, digital control, and digital processing DSP is needed. That's where you want to put these CMOS elements. But up front in the LNA, the PA, the mixer, they often don't offer the performance that you need in these bands. Yes, you can make them work, but they don't work as well as the 3.5s. And that's where the heterogeneous requirement really comes from. You use the 3.5 mimics up front for bandwidth, for linearity, for PA power, and for low noise LNAs and mixers. To give you an idea of, you know, really why you want to use as much silicon as you can. Now, this is a bit dated. This is a Lockheed Martin X-band phased array that they presented back in 2010. That was, you know, really prior to the RFIC revolution. And you can see here in this center photograph that the gas chip, which did all of their RF processing, is on the right, and it was married to a digital control chip on the left. The two were wire bonded together. And this was a, you know, very complex and very heroic design, but it was still quite large, even though they integrated as pretty much the entire RF front end onto that gas chip. It was still big, and you could do much better today with a SIGI chip. Same complexity as the gas chip, but a fraction of the size is shown by that teal square at the bottom. And on top of that, if it's SIGI by CMOS, you can also put in the digital control as well and get rid of that second chip altogether. So, you know, this was really the driving force behind a lot of the cost reduction in phased arrays. And it's really why you have to have silicon in your phased array, even today. On the other hand, let's look at power amplifiers. This happens to be a line of indium phosphide HPT sub-millimeter wave, millimeter wave power amplifiers that Teledyne sells commercially. And these performance numbers here that we achieve with indium phosphide HPT technology are really state-of-the-art and cannot be beat using other technologies at this time. So you want to be able to access, you know, these two worlds. You want to be able to access silicon where it makes sense. You want to be able to access 3.5s where it makes sense. And just a little case study here. This was a look at a W-band phased array where we compared a pure silicon solution, which is called SIGI here in the column, and a hybrid SIGI indium phosphide solution, which is labeled indium phosphide in the column. And what we found was that if you went with just a pure SIGI solution, which we actually initially designed, we came up with a figure of merit based on output power, noise figure, and power and DC power dissipation of about 1.6. And moving the front end to indium phosphide, in other words, replacing the PA and LNA with indium phosphide, but keeping the rest of the circuitry in silicon, we got roughly an 18 times lower, essentially lower power dissipation for the same performance. And so that was really, you know, an eye-opening discovery that, you know, the power of merging these two technologies or merging 3.5s with silicon is really very critical, particularly as you go up in frequency, W-band and higher. Another area where heterogeneous integration makes a lot of sense is in tunable broadband transceivers, typically EW-based applications. But here, again, you want to use fast 3.5s on the front end, LNAs, VGAs, also the output DACs and the track and holds on the receivers. These all benefit through having very fast access to 3.5 technologies. The PA is typically going to be gallium nitride for many applications. That will transition to indium phosphide as the frequencies get really high. But for 50 gigahertz, you'd certainly be looking at gallium nitride for that output PA. But the center section, the DSP, the high resolution ADCs running at reasonable speeds, 2.5 gigasamples per second, this is all going to be low power dense CMOS. And you really want to be able to marry all of these technologies together, stitch them together with very high performance interconnects and good thermal properties in a packaging solution that can support heterogeneous integration. Okay, so let's now look at the 3D-HI SLIC foundry process that Teledyne has and is intending to offer through the California Dreams Hub. So this is kind of an overview of what it's all about. It's a batch fabricated, which means it's fabricated on wafers, packaging technology that's optimized for millimeter wave phased arrays. It's designed to integrate heterogeneous chips. So any chip, silicon, indium phosphide, gallium nitride can be accepted in this packaging solution. It supports planar radiating elements on the top, which would be critical for a phased array application. It has good thermal management. You can get the power out of these chips through the bottom of the tile. And it supports an RF interconnect, both through substrate vias for backside signal access and a 4-layer RDL on the top, which has IC grade fine line interconnects. So 10 micron line in space and 10 micron vias. The approach has been validated through a number of phased array demonstrations over the years. And we have spent 10 years improving the manufacturing readiness level of it, including Air Force sponsored Mantech. And it is today offered as a Foundry service at Teledyne and has a Cadence SDK, as well as ADS models as well. Key features of SLIC: low loss impedance controlled transmission lines, fine line geometries to support dense compact interconnects, heterogeneous integration of RFICs, MMICs, antennas, transmission lines in a 2.5D environment with good thermal properties, through substrate vias for backside signal access, and batch fabricatable to minimize touch labor and support scalability, particularly for arrays. This chart shows the architecture of the SLIC subarray tile. So at the bottom, labeled silicon interposer, this is a micro-machined silicon wafer where we etch pockets of a very precise size to match the RFICs and MMICs that you wish to insert into the package. Through substrate vias are also etched through the silicon interposer to allow signals to transition from the back to the front of the tile. Once those RFICs and MMICs are placed in the recesses, that's done using an automated pick and place tool, then we planarize the surface using a BCB material and CMP to get a flat surface on top of these buried die. And then we build upon that a 4-layer interconnect. That interconnect is essentially BCB and gold, same as our indium phosphide HBT process. And then on top of that, optionally, you can place the antenna. That can be either glass or Kapton based substrate. This shows some detail on design rules and also dimensions of the process. Cross-section of the interposer plus the RDL on top of it is shown. And also some of the key process dimensions are shown in the table as well. And this allows you to assemble, integrate known good die, because you can test all of your RFICs and MMICs prior to insertion into this technology for the final packaging, just like you would do in a regular packaging solution. The first SLIC tile was demonstrated back in 2012. This was a 44 gigahertz transmit and receive phased array. Used a silicon beamformer that was designed by UCSD, Gabriel Reviz's group, and it used indium phosphide PAs that were designed here at Teledyne. It was on a lambda by 2 element spacing at 44 gigahertz and had a 4x4 radiating elements that gave a pattern as shown on the right. In terms of the size, this was a very thin, basically a chip in the finished product. It was a millimeter thick and about 12 millimeters width and height. And that supported 16 half-wavelength elements. Looking at a little more detail at the micromachined silicon interposer, you can see that the cavities that were etched in the silicon to support the chips that were being integrated were very finely etched, and you can have separation of chips less than 100 microns. So those wall thicknesses between adjacent die can be as small as 100 microns. And that permits very dense integration of the MMICs and RFICs. Through substrate vias are copper-based and go through the interposer from top to bottom. They're about 70 microns in diameter, and the total thickness of the interposer is typically around 600 microns. The third diagram, I don't know if my pointer shows up, but the third photograph shows a buried die after being planarized with BCB on top, and then an RDL is placed on top of that. And the final photograph shows a X-ray of the, in this case, an indium phosphide PA buried inside the tile. And they're built in batches on wafer, just like you'd build an integrated circuit, MMIC, or an RFIC, which reduces cost and increases production quantities, allows you to scale up to higher quantities without requiring a lot of touch labor. So in this particular sample here, we have, I think it's 19 tiles, and once they're fabricated, they get diced out as individual chips. The SLIC process was subject to a MANTEC about 10 years ago from the Air Force. And the intent of that MANTEC was to improve the MRL level. Started out at 4, and by 2018, it had reached 6. And, making processes transition from R&D demonstrations to actual foundry processes that you can offer to a customer with an expectation of reasonable yields and cost is something that does take a substantial effort. And through this MANTEC, we were able to address yield limiters that were a problem for the initial R&D demonstrations, and also allowed us to move that back end of line into basically from an engineering step to full production process modules with process control monitoring, statistical process control, and work instructions suitable for fab ops trained staff to reliably and reproduce the process. Process flow itself is fairly straightforward, but it's not a trivial effort at all. It starts with fabricating the through substrate vias in the silicon wafer. That's the first step. We then micromachine the recesses to hold the chips and do the initial planarization once those chips are placed inside the recesses. And that's followed by standard MMIC type interconnect buildup, 4 layers of gold and BCB. And that's optionally followed by a UBM on the top or the bottom, depending on the particular application for the die. And then finally, on wafer testing of the finished product can be done, and then the parts etched and diced out for final delivery. And I should add that the ability to test on wafer does bring with it some additional benefits in terms of reducing test costs and increasing throughput for test as well. A little look at some of the fabrication yield limiters that we had to address during that manufacturing improvement process. From a cartoon point of view, you start with your interposer etched to accept various RFICs and mimics. Those are placed into the recesses, and then a planarization coat is placed on top of it, CMP'd flat, and then you build up a standard RDL on top of that. So particular concerns for this process, the die placement accuracy. When you place the die in the holes, the pads need to line up so that your subsequent connections to it can be made reliably. The die pad height, the height of the pads on the buried die needs to be uniform so that you can reliably drop vias down on top of those pads. And the BCB planarization itself needs to be flat, crack-free, and reliable, and addressing the stress of that planarization process is a critical step in getting that outcome. So for die loading, we use an automated pick and place tool, and you can do hundreds of tiles per wafer. And the pick and place tool is very good for improving die height uniformity, which is a critical metric for tile yield. So in this particular demonstration here, what we have is a silicon beamformer, which is a larger chip, and 4 indium phosphide HBT PAs. Together, each of those formed a 4-channel tile, which was the intent of this effort. And so this shows a loaded wafer after planarization has been completed. The tool we use for this pick and place is standard die attach. This one's made by Datacon and has placement better than 10 microns. And it also has the ability to dispense an adhesive. We use BCB. And also to maintain a very good placement of the die in terms of location, angular mismatch, and so on, as it uses cameras and recognition algorithms to ensure that the chips go reliably into the recesses. I'm going to try and show a video here of the pick and place in operation. So what we do first is a pre-dispense, and now what's happening is that this dispense gun here is putting adhesive in each of the recesses. And so this is the first step of the die placement process. Once that's completed, the wafer is sent out for visual inspection, which is happening right there. And then the next step is die placement. So we pick up a die from a gel pack, we place it on a post and examine its position, orientation with cameras, and then the die tool picks that up and places it into the recesses. So here it is picked up, inspection, and drops into the recess. Picks up another die, inspects, drops into the recess. And it repeats that until all dies are placed. And so this process is efficient and quick, and scales nicely to high volumes of parts. And then once that's completed, the wafer is sent out for inspection and then planarization. So as I mentioned, die height after chip load is a critical parameter. We measure it using a automated Brooker tool, and then plot that die height and check it for tolerances and yield. We try to get 95% of them within our limits per maximum and minimum die height. As I mentioned, in addition to the process, there has to be a design kit so that customers can access the technology, simulate it, and design into it and meet our design rules. So we have both a cadence design kit and a preliminary ADS, Keysight ADS design kit as well. And that significantly improves both the customer's final design compliance with our design rules, and also in terms of simulation of the expected package performance versus what you actually get. Automated test is another option that, because the finished product's on wafer, you can use standard pick and probe station, automated probe stations to do an RF compliance test after fabrication and before dicing to screen out bad chips and to confirm performance. And finally, the option does exist to place an integrated planar antenna on top. We have two approaches. One uses a capped on film that we can etch into blocks and place metal on top of it. And another approach is to use a glass substrate, perhaps one from Mosaic or another outside vendor. You can use either of those approaches, and then we can basically bump those to the top of the tile. And finally, I'll finish up with a couple of examples of phased arrays that we've built. 3 of them were DARPA programs: W-band multifunction RF program, DARPA video synthetic aperture radar program. Both of those, both the VISAR program was 220 gigahertz, and obviously the W-band program was W-band 94. And then most recently, we've been using this technology to demonstrate arrays for the LGAR program, which is also a 220 gigahertz program. So the MFRF program was really designed to see through fog and dust for helicopters primarily. And the idea was to build a phased array for that platform that could be used both for radar applications when wanting to see through, fog and dust, particularly for landing, and then switch it over to comms when you're in flight and need to communicate with other people. So that was the vision of the MFRF program. Teledyne built 325, basically 64 element tiles for this program. Each tile had both transmit and receive and vertical and horizontal polarization. So it was a very complex chip, 256 elements, channels, I should say, 64 elements, transmit and receive. And that was all done on a SIGI platform. So we didn't use heterogeneous integration for this application, but we were able to make an extremely complex phased array chip on SIGI and then integrate that using SLIC into these tiles. And we were able to also test these on wafer as well at W band. So it was a very challenging but ultimately successful demonstration of SLIC. BISAR was another use of SLIC. Here we used vanadium dioxide phase shifters to make a reflect array that could be programmed at 220 gigahertz for scanning a SAR signal. And finally, ELGAR, which is an ongoing program here, is demonstrating a 220 gigahertz phased array using very advanced indium phosphide technology to get very high efficiencies. Greater than 25% PAE has been demonstrated at 220 gigahertz. Okay, so I'll wrap it up. I think there's a few minutes left. But to conclude, we have a SLIC packaging solution that provides a versatile approach to packaging of heterogeneous millimeter wave and submillimeter wave integrated circuits, targeting primarily millimeter wave transceivers and phased arrays. It integrates antenna through substrate vias, bump pads, MMICs, and RFICs, and their interconnects into a single compact 2.5D package using a micromachined interposer. It's offered as a Foundry process with a design kit, and we intend to offer it through the California Dreams and are working to make that happen now. And it enables next generation planar phased array sensors and millimeter wave digital transceivers. And just an acknowledgement, a lot of this work was funded by DARPA and the Air Force, and we appreciate their support. So at this point, I think we can entertain questions, or maybe Steve can tell me what the next steps are.
Yep, that's right. Well, our first step is to thank you, John, for the excellent presentation, and we'll have a round of virtual applause, but yes, we can take questions. And there is a question in the chat. Andrew Ketterson from Corvo, you're welcome to come off mute and ask it if you'd like, or if you don't come off mute.
Sure, I can come off mute if you can hear me.
Yep.
How high a frequency can your TSVs support with reasonable insertion loss? And I have two other questions to follow up then.
Yeah, so what we typically do with the through substrate vias is synthesize a coax using a ring of ground vias and a center hot via. And using that approach, we can get up to 50 plus gigahertz is reasonable.
And over what bandwidth can you do that? I mean, in order to go up to 50 gigahertz, do you have to have it tuned very?
No, it's not tuned. So, of course, there's a transition that has to be managed both off chip, off tile to your printed circuit board, presumably, and also potentially the same transition to the MMIC buried inside. But those can be managed, and you can get, there's no bandwidth other than the upper band. So you can do 0 to 50 gigahertz. And typically, these interconnects are broadband IF and less broadband LO signals that are being fed into the tile for up conversion to the final operating frequency in the tile itself.
And
so
that's with those 750 micron thick silicon, right? Or 700,
not that
you
thick.
said.
It's typically 625.
Okay.
John, this is Gabriel. Can you go to your cross-section of the SLIC process? Yes, like this one. Yeah, I feel you are not giving the technology the, how do you say, the light that it deserves. For me, there are two things. One is you don't need really antennas or anything. On the top metal layer, you can put bumps. And this technology is great for multi-chip modules all together, interconnected together into a multi-chip module. And then you can take this and bump it on top and then flip it on yet another carrier. And these modules could be partly digital, like ADCs and DACs, and partly analog, and so on and so forth. But what's great about it is that the silicon is a great heat conductor. You do have multi-chip modules which are done using interposers, but here you can put PAs and you can take the heat out from the back. And when you flip it, you have a pure access to take the heat out from the back. So I think the SLIC has also a whole different path in high power packaging and for PR modules and other. There are many other processors that consume immense amount of power, and I don't think you are limited to 4 metal layers. You can have 5 or 6 or 7. With development, you can have more metal layers for a lot more interconnects too.
That is true. Yeah. Thank you for those comments. We have bumped MMICs on top of the tiles, and that's fairly straightforward. And therefore, it follows that you could invert it and bump it to a printed circuit board just as easily. So yeah, I think you make some good points there. Thank you.
What size wafers did you say you were doing the SLIC on?
These are done presently on 4-inch silicon, but that's primarily because the quantities of parts that our customers have needed have not really warranted going to a larger wafer size.
Sure.
And that's sort of endemic in the DIB world. The volumes aren't often that large.
Do you think you'd have warpage issues as you started getting large? You must already have a fair amount of stress there. Now you've got a thick substrate that probably helps you, but
yeah, you certainly have to manage the stress, and we haven't demonstrated the process on larger wafers, so that would presumably take some development.
The stress is only, you're saying, coming because you're using BCB or so on, but you could take all this PCB layer and send it to a regular silicon glass backend with copper Damascene process. And then you will remove all of these stresses, and you can grow to 12-inch if you want to.
Yeah, that's true. And I should add that with regards to more layers, we have, under the Elgar program, added a copper Damascene back end of line to the HBT process, and that could transition to SLIC as well.
although you've got some fairly thick layers here with the BCB that.
Yeah. Now that's intentional because to get low loss millimeter wave transmission lines, those thick dielectrics are helpful. They're not a requirement in the sense that we can go thinner, but for the application space that we were targeting, the thicker BCB was advantageous for lower loss transmission lines.
But might be a bit of a challenge if you move to glass TS, although maybe people are doing things that thick, but that seems thick to me for TS. And
I would agree with you. I think generally speaking, the industry doesn't make layers that thick.
Yeah, 2 to 3 micron is standard in industry, but not that thick. In any case, in my opinion, it is the etching in the silicon and putting the chips at a very tight pitch. Anything above the silicon is easy stuff there. that's very easy, and how much heat you can take out. I mean, that's what's very exciting about this technology. For me, I would use it, forget Steve and AJ and whatever, go sell it to NVIDIA for high density, high power packaging of multiple chips, and that will be, that will be a great way of doing, very high power processors and TIA drivers and so on and so forth, all into a single package.
Okay, we have time for one more question. Avantika has patiently had a hand up.
Hi, Steve. Hi, Jonathan. And thank you for a great presentation. Just a couple questions. One, is there a limitation on the die size that you integrate? Is there a largest possible
Yes.
die size?
So our current stepper is limited to 18 millimeters. And so going to tiles bigger than 18 millimeters is not something that we have done at this point. Now, it's possible you could go to a contact mask to get around that limitation, but we haven't done that.
I'm sorry, my question was chip size that you integrate. So not the final product size, but the recessed die that you've placed in there, right? Is there a limitation?
Yeah. So basically, as long as you can maintain a, say, 100 micron fence between adjacent tiles, you can use pretty much the entire tile area for the buried part. And under the Midas program, Raytheon embedded a very large chip in that basically took up almost the entire reticle. They just left space around the perimeter for through substrate vias. So, it's really a balance of what do you want to use the available area for. If you have to get signals to the backside, then you're going to need to devote some of that tile area to through substrate vias. What's left over you can allocate to buried die, and the wall thicknesses, as long as they're bigger than 100 microns, you should be fine.
Another question I had was distance of TSV from the etched cavity. What's the minimum distance of TSV from
how
the
far?
edge?
I don't remember that design rule, but it's probably on the order of a few hundred microns.
So like over 200 microns or so?
I'm thinking it's actually something like 160, but I'm not sure.
Okay. Thank you.
Okay, thank you again to John for the great seminar, and for to the audience for participating and the great questions at the end. Just a reminder that this seminar series happens every week, and there's a QR code if you'd like to get notices of future seminars, and we have our YouTube channel, and you can like and subscribe to videos there. I think we're close to 2,000 views total for all of our seminar series, so we're very happy that the word is getting out. And then finally, we will end on this lineup of our upcoming seminars. We have Subu and Chewy from UCLA both the next 2 weeks. The week after that, we're off for Memorial Day. The week after that, Min Nguyen from HRL, and then we'll see what we are going to do starting in June. So thank you, everybody, very much, and we'll see you soon. I will also say we're looking forward to offering this technology that John talked about through Moses 2.0. So glad to be able to work together on that. Thanks, John.
Thank you, everybody. Appreciate
Thank you, John.
tuning in.